Hey folks, continuing on right where we left off and reviewing some of those learning goals, okay? So I spent a lot more time going over the combined gas law as well as the ideal gas equation, okay? And so being able to solve for any variable PV, N, or T given a set of data. But 90+% of the time when we use the ideal gas law, we're really solving for the number of moles. It's another way of getting the number of moles so we can do reaction stoichiometry problems. Okay, and so this also goes along with being able to perform dimensional analysis calculations of chemical reactions involving gases. We're going to do this more, like I said, in discussion. Okay. So on this next video, I'm going to be talking about the next 3 learning goals, 6, 7, and 8. And then after that, it'll be one last 4th video. Okay. So here we go. So gas density. So I'll start here with this graph that I have. And note specifically, this is helium. Okay. So as it turns out, in the ideal gas equation, PV equals nRT, there's nothing in that equation that says specifically what gas it is, because it's the ideal gas equation. We assume all gases behave the same. However, as we start to look at gas density, we will actually start to see some differences between the gases. Not all gases have the same density, because not all molecules have the same mass. Okay? And so I'll remind you, density is mass divided by volume. Okay? And so then we also notice this helium density, not only is it quite small, but look, it's decreasing with increasing temperature. And that's true for all gases. Why? Okay. Well, look, density is proportional to 1 over volume. Okay. That's also true. But what's going on as I increase the temperature? Okay. Well, we have to remember Charles' law. Temperature is directly proportional to volume. So if I get something hotter, if I heat something up, it expands, right? And so if we're talking about the same mass of material, right? Like let's say I have a balloon with some helium in it, okay? The mass inside that balloon is going to be fixed, right? So I'll draw back to my little balloon here, okay? So the mass, I'll say M1 and V1. And so now let's say I add heat. Okay, well, we know that the volume is going to get bigger, but look, it's still the same mass. M1, actually, let me write 2 just to be consistent with our other nomenclature. I'll write a 2 here. Look, M1 equals M2 because we didn't change the mass of gas in the balloon, right? It's the same amount. However, the heat is making the balloon expand, so that means the density has to decrease, right? If the volume here is going up, but the mass is staying the same, 1 over a bigger number means the density has to go down, okay? So gas density always decreases with increasing temperature. And that's actually a big reason you can explain a lot of stuff in meteorology and weather, right? Hot air parcels will rise, okay? Or in other words, as an air parcel or some mass of air, right, as it is heated, it will rise because its density is decreasing. This is why hot air balloons work, right? You heat up the gas inside the balloon and it decreases the density. It decreases it to be less dense than the atmosphere, and that sucker will float, okay? And this is kind of related to my next little question here. The average molar mass of air is 28.5 grams per mole. Based on this, which gases do you expect to sink or float? So air, I'm gonna start exploring this more in this video, okay? Air is a mixture of nitrogen and oxygen predominantly, okay? But also there is a little bit of argon, there's a little bit of carbon dioxide, there's some water, there's some methane, there's all kinds of stuff in air, okay? The nitrogen and oxygen, as we'll see, is about 99% of that air. But all the same, there's all of this stuff in air. And that's why it has some average molar mass, right? Because we have, an exact molar mass of each of these compounds, right? Nitrogen, we know, is 28 grams per mole. Oxygen is 32 grams per mole. Argon, let's see, I don't have that one memorized. Argon is close to 40 grams per mole. CO2 is 44, etc. So it makes sense that the molar mass of air is just a little bit more than nitrogen, right? Okay, so here's a picture. So here's the results. So if I had a balloon containing helium, nitrogen, and carbon dioxide, just as examples, and this is all in atmospheric pressure, so we'll say all at, let's say, 298 K, and let's say 1.00 ATM. So these are the numbers for these conditions. The helium balloon would float, but the nitrogen and carbon dioxide would not. Okay? And you can see here what the densities are. So how do we get to these densities? Okay? Oh, I lost my cheater page. Okay? So we know that density is mass divided by volume. Okay? Let me say little mass. And using the ideal gas law, so I'm gonna turn to my cheater page just to make sure that I get the numbers and everything correctly. 1 second here, I'm finding it. Okay, bueno, here we go. Okay, so we know density is mass divided by volume, right? So if we just for now assume, let's just say we're talking about 1 mole of these gases, okay? So, and then suppose we have 1 mole of each gas, right? So then that means my mass is just going to be the molar mass of these things. And how do I calculate my volume? Well, I remember PV equals nRT, okay? So volume, and really what we want is, I'll solve for volume, excuse me. So volume we know is nRT divided by P, okay? And so if I plug this in to right here, all right, then what I end up with is the following. I end up with the mass of this object, so we'll say density equals. So density equals the mass of this object, and now I'm going to divide it by all of this, nRT over P, okay? And when I do some algebra and rearrange this, I recognize 1 over P is just P. So this becomes P, and now I'm going to separate this out, and I'm going to say M divided by N all over RT. Well, this quantity M divided by N is, I'm going to use this like cursive-y looking M that the book uses, right? That is the molar mass, the mass divided by the number of moles, okay? So I can easily calculate the molar, I can easily calculate the density of any gas using this equation. And so I told you the average molar mass of air is 28.5 grams. So let's calculate the density of air, okay? At 1 atmosphere and 298 Kelvin, right? So that's going to be so P is 1.00 ATM. We're going to use the average molar mass of air, 28.5 grams per mole. R is 0.08206 liter times atmosphere divided by mole times a Kelvin. And then for 298 Kelvin, all of this is going to give me the density, and that's going to be the density in It's going to be grams per liters. Check it out. So ATM and ATM cancel, Kelvin and Kelvin cancel, mole and mole cancel, and I'm left with a number in gram per liter. So that's going to be 1 times 28.5 equals 28, oops, too many times. Start over. So 1 times 28.5 equals 28.5. Divided by 0.08206 equals, and then divided by 298 Kelvin, haha, with, let's call it 3 sig figs, I get 1.17 gram per liter for the density of air. Well, check it out. A balloon of just pure nitrogen is 1.19. So as small as that is, that means a balloon of just pure nitrogen will sink. A balloon containing pure carbon dioxide, right, that's 1.86 grams per liter. That will definitely sink. But look, helium is like almost 10 times, that's grams per liter. It's almost 10 times less dense than air. Similarly, hydrogen, okay? So hydrogen and helium are really the only gases that we typically can get our hands on that will float in air, okay? But also we note that in a hot air balloon, you could put air. You don't have to put just helium in the hot air balloon. You could just put regular old air. And as long as you're heating up that air, it's going to become less dense and it's going to float, okay? And so now this gets us into Dalton's Law. It's Dalton's Law of partial pressures and mixture of gases, right? And we've just been talking about that, right? For example, Dalton's Law says if I have some container, and I love drawing balloons, right? So suppose I've got a balloon, and in this balloon are a whole bunch of gases, okay? So I'll say P tote, okay? The total pressure inside this balloon is going to be the sum of all of the individual pressures of whatever is in there, okay? So for example, suppose we put atmosphere in the balloon, right? Which could be achieved like through a pump. Not me like blowing it up, like putting my breath, but let's say I'm putting the actual atmosphere in the balloon with some bike pump, right? Pump it up, okay? Well, that total pressure would be, let's just call it, 1.00 ATM, assuming we're at sea level and it's perfect conditions, okay? Well, as it turns out, about zero, actually I'm going to take one significant digit off because I just realized I don't have all of these digits committed to memory. 1.00, okay? Well, as it turns out, nitrogen would account for about 0.78 of that at sea level, at the atmosphere. At sea level, nitrogen is about 0.78 atmospheres, okay? Oxygen is about 0.21 atmospheres. This plus this gives me 0.99. All of the other stuff in the atmosphere, the argon, the carbon dioxide, the water, all that other stuff contributes about 0.01, okay? And so we could, that's why I took away one significant digit, right? If I had 3 sig figs, then I would actually start to see more precise numbers for all of these other things, okay? But in any event, the pressure that we get in the case of the atmosphere, for example, is a sum of the pressure of all the other individual components. And this is actually where you get the average molar mass of air, okay? From the fact that about 0.78 is nitrogen, about 0.21 is oxygen, and about 0.01 is all this other stuff, okay? And so there becomes a really easy way to use these numbers in calculations. And that's called the mole fraction. Okay, and I want to note that mole fraction is not only important for gases, it's also important for liquids. Or really any mixture. Okay? So what the mole fraction says, and so mole fraction gets the Greek letter chi. I know it looks like an X, and if you use an X, that's fine. Technically, it's the Greek letter chi. Okay? And what the mole fraction says, chi of whatever, species number 1, right? If I do this generically, like, P1, so 1 could be nitrogen or oxygen or carbon dioxide, whatever, 2, 3, 4, 5, etc. Okay? So we could have the mole fraction of thing number 1 is going to be the moles. So how many moles of that thing there are divided by the total. Okay? And as it turns out, in ideal gases, this is pretty cool. The mole fraction also just equals the pressure fraction. Okay? So for example, the partial pressure, so when we start to write these things, we call these partial pressures. Okay? Partial pressures. And obviously this is the total pressure. Okay? So I just told you the partial pressure of nitrogen at sea level is 0.78 atmospheres. Okay? 0.78 atm. Okay? What's the mole fraction? Well, automatically, I know that it's got to be the exact same thing. So the mole fraction would also be 0.78, and I'm going to write this as chi N2. Okay? So this works out really easily for gases. Now when we deal with liquids, the mole fraction, it's not so straightforward, okay? So it depends on density and so on and so forth. But for gases, this is really straightforward. Whatever the partial pressure is, it's going to be the same as the mole fraction, which is pretty cool, okay? And so this is how you get the average molar mass of air. It actually comes from the fact that you have 0.78 as the mole fraction for nitrogen times 28.00 grams per mole plus the mole fraction of oxygen. So I'm going to say this is chi N2. This is chi O2 is 0.21, and the molar mass of that is 32.00 grams per mole. And if I just use those two, I know we've only considered, we've only got 0.99 of the fraction, but if we just use those two, let's see, so 0.78 times 28 equals that, plus 0.21 times 32 equals that, 28.56. And really, I was kind of cheap on my sig figs back there. I probably should have used maybe like 28.6. Okay. Right, so but from there you can see I get 28.56 grams per mole. And of course, if we added the other 1% of those gases, I'd have an even more refined number for the average mass of air. Okay. So we can use these mole fractions as an easy way of doing calculations in mixtures. Okay. So here's another sample problem that's kind of cool for any of you who are scuba divers out there. Okay. Scuba divers who descend more than 45 meters below the surface may use a gas mixture called trimix to support their breathing. One type of trimix mixture contains 11.7% helium, 56.2% nitrogen, and 32.1% oxygen by mass. Calculate the mole fraction of each gas in this mixture. Okay. Well, whenever we have these mass percentages, right, I'm going to assume, you guessed it, 100 grams. Okay. And if that were the case, I would have 11.7 grams of helium. I would have 56.2 grams of nitrogen, and I'd have 32.1 grams of oxygen. Okay? And so now the first thing we got to do to get mole fraction is calculate how many moles we have. Okay, so the molar mass of helium is, we'll call it 4.00 grams of helium in 1 mole. Nitrogen, I'm just going to call it 28.00 grams of nitrogen in 1 mole. And oxygen, 32.00 grams in 1 mole. Okay, I'm going to rely on my cheater notes here to just get this calculation done. But you should verify that it works out. So this becomes 2.92 moles. This becomes 2.01 mole. And this becomes 1.00 mole. Okay? So now, what do we do from here? Well, I have to recognize, for example, if I want the mole fraction of, let's say, helium, then I need the number of moles of helium divided by the total number of moles. Same with nitrogen, same with oxygen. Okay? So how are we going to do that? Well, I know helium was 2.92 moles. So what's the total? Well, the total is going to be 2.92 plus 2.01 plus 1.00. Okay? And that all gives me 0.493 for the mole fraction of helium. Okay? And so now what about the mole fraction of nitrogen? Well, once again, that's going to be the number of moles of nitrogen divided by the total number of moles. And the mole fraction of oxygen is going to be the number of moles of oxygen divided by the total number of moles. Okay? So I'm just going to cut straight to the chase and give you the numbers. So for nitrogen, I get 0.338. And for oxygen, I get 0.168. And here's how you know if you did this correctly. They should all add up to, you guessed it, 1.00. Okay, 0.493 plus 0.338 plus 0.168. Beautiful. 0.999. Okay, close enough, right? Some sig fig situation happened there. So now, why is this useful, getting this mole fraction? Well, the reason why this is useful is because suppose instead of knowing the percent by mass, what if I wanted to know how much pressure there was of helium, or how much pressure of nitrogen, or how much pressure of oxygen, right? Well, now all I need to know is the total tank pressure, right? Whatever, how much pressure is in that tank. Let's say it's 2,000 psi. And then it doesn't even matter what the units are. I can literally just now say 0.493 times, let's say that 2,000 psi, and that would tell me how much pressure there has to be in helium. Okay? So all of these are ways of just converting units, right? From mass units to mole units to pressure units. Okay? And so let's see. I think that's a pretty good place to wrap it up. So once again, gas density and mole fraction and Dalton's partial law. It's Dalton's law of partial pressures. It's kind of all about dealing with mixtures of gases. Okay, folks, I will see you in the last and final video for gas laws.